We all know that speakers are for emitting sound. But have you ever brainstormed wildly? Is it possible to use the principle of speaker vibration pushing air to help cool down your phone? Sounds crazy, right? One is auditory enjoyment, and the other is thermodynamic engineering. The two seem completely unrelated. But if we return to the essence of physics, what is sound? Sound is actually vibration waves of air. And what is wind? Wind is the flow of air. If we could create a special kind of speaker, where the diaphragm vibrates fast enough and the energy is concentrated enough, what it produces is no longer just sound pressure, but actual air pressure. This was originally just a crazy physics hypothesis, until a company named xMEMS Labs unexpectedly turned it into reality. This company was originally an outlier in the semiconductor field. They were dedicated to using silicon chips to make solid-state speakers, attempting to eliminate the bulky coils and magnets in traditional headphones. But during the R&D process, engineers discovered an interesting phenomenon. When these micron-level membranes vibrated violently under certain conditions, besides emitting sound, the chip actually generated a steady airflow around it that could not be ignored. This discovery made them realize that the potential of the technology in their hands was far more than this. Thus, they made a bold decision: no longer let this chip sing. They pushed the vibration frequency to ultrasonic bands, completely inaudible to the human ear, and redesigned the microfluidic chamber structure. This speaker, which was originally meant for headphones, transformed, becoming the world's first chip-level solid-state fan, xMEMS XMC 2400. It completely abandoned the motors and blades of traditional fans, using the inverse piezoelectric effect to pump the internal MEMS membrane at high speed. Don't let its fingernail size and 1 millimeter thickness fool you. It can generate an astonishing 1,000 Pa, a back pressure at a microscopic scale. This means that even in the high air resistance environment inside a phone, with almost no space for convection, it can still forcibly squeeze the hot air out. This is not an ordinary chip. Although it looks like a standard packaged IC on the outside, its essence is an out-and-out active cooling fan. The fans we are familiar with, whether powerful desktop fans or laptop centrifugal fans, all have a core structure of motor plus bearings plus blades. This mechanical structure has insurmountable physical limits. Once shrunk to a certain degree, bearing friction becomes too high, blade efficiency drops to zero, and they cannot be waterproof. But this technology from xMEMS completely solves these problems. Why are electronics engineers excited about this technology? Besides cooling, what's more important is the manufacturing revolution. First is the compatibility with SMT reflow soldering. Traditional microfans are mechanical parts, requiring workers to fix them with screws or glue on the assembly line, and plugging in cables, which increases assembly costs and risk of damage. But xMEMS is a semiconductor component that supports SMT surface mount technology. This means it can be like capacitors and resistors, placed directly onto the PCB by machines and fixed through a reflow oven. For large-scale automated production, the efficiency improvement is massive. Second is the secret of the IP58 protection rating. Mechanical fans fear water and dust the most, because once dust gets into the bearing, it seizes up. But the XMC 2400 is essentially a solid-state structure. Its vibration unit can be completely sealed to achieve an IP58 rating. This makes it the world's first fans that can truly be used in waterproof flagship phones. Speaking of solid-state cooling, we must mention another strong competitor, Frore Systems' AirJet, although both use the principle of membrane vibration. In terms of product philosophy, they have taken completely different paths. We can analyze this in depth from 3 dimensions. First is the game of energy density. AirJet's goal is to replace laptop fans, A single unit can remove 5.25 W of heat, with back pressure up to 1,750 pascals. Its strategy is system-level cooling, attempting to blow strong airflow through the entire heatsink module. xMEMS, however, aims to solve local hotspots. Its size is only 1/40th of AirJet. It's not trying to cool the entire machine, but rather to attach directly on top of the SoC processor or modem chip, precisely targeting that hottest spot. Second is the math of power consumption, which is the biggest watershed between the two. AirJet consumes about 1 W of power during operation on devices with large batteries like laptops. This is acceptable. But for mobile phones, 1 W of power consumption is itself a huge heat source. If you generate 1 W of heat just to cool down, the loss outweighs the gain in low-load scenarios. Moreover, phone battery voltage is usually 3.8 volts. 1 W means a current consumption of about 260 milliamperes, which is a huge burden for a phone. In contrast, xMEMS consumes only 30 mW. This is almost negligible. It allows the phone to enable cooling even during standby or light loads, without causing battery anxiety. Finally, the flexibility of physical layout. AirJet requires a dedicated air duct design and occupies a larger volume. xMEMS is only 1 mm thick, so phone manufacturers can flexibly distribute 2 or 3 xMEMS chips on different heat sources of the motherboard. For example, one on the CPU, one on the 5GRF chip, achieving partition thermal management. So why do we need this kind of active cooling? Why are existing VC vapor chambers not enough? This involves the stationary air boundary layer in thermodynamics. Current flagship phones, although they have huge VC vapor chambers to conduct heat to the back cover, once the heat reaches the surface of the back cover, since air is a poor conductor of heat, and the air layer clinging to the surface is often stationary, heat is difficult to dissipate into the environment. This is why the phone back cover feels hot, but the core temperature still doesn't drop. xMEMS does more than just blow air. It's pulsed. Airflow can effectively disrupt this stationary boundary layer, increasing heat exchange efficiency by several times. According to tests, it can reduce the phone's surface temperature by 4 to 6 C. This doesn't sound like much, but in the semiconductor field, this is enough to determine if the processor stays at full performance or enters thermal throttling protection. The emergence of this technology will unlock many product forms previously limited by thermal design. First is our VR smart glasses, which is the killer app for xMEMS. Glasses sit close to the face and have zero tolerance for vibration and noise. xMEMS's silent and vibration-free characteristics makes it the only currently viable active cooling solution. Second is high-speed M to SSDs, as read-to-write speeds break limits. Controller temperatures become extremely high. xMEMS can be integrated directly under the SSD heatsink to prevent driving throttling. Finally, of course, are AI phones. When phones need to run on-device large models for long periods, continuous low-power active cooling will become essential. xMEMS expects to sample to Tier 1 customers in Q1 to 5. This means that as early as the end of 2025 or early 2026 flagship products, we can witness this silent cooling revolution. Cooling has finally entered the semiconductor era.